Okay, so we start a new lecture again. So this is lecture number 20. So what we started in the previous lecture was, so let me just give you a recap. So we started our discussion on what we called as phase rule, and phase rule is basically a equation that we'll come up with, which relates the number of phases in a system, number of components in a system, with the total number of independent variables that you can have to predict the phase equilibrium. So we began this by considering a multi-component system. So in that, total number of variables are temperature, pressure, and all the components. So you have, let's say, C number of components. So total number of C number of components make up P number of phases, let's say, in a given system as a function of various conditions. So total number of possible variables is nothing but C into P plus 2. Now, how do we now limit the how do we find out what is the total number of independent variables in these, out of this Cp plus 2 number of total number of variables? This requires us to consider two things. First, the concept of mass conservation in a given system. Second is the concept of chemical equilibrium in a given system. So this is going to be determined by, so basically we are going to relate independent variables, phases, and components, and this is going to be based on conditions of mass conservation and chemical equilibrium. So we saw that total number of variables was equal to Cp plus 2, and then from mass conservation it follows it's not conversation, it's conservation. It follows that number of constraints. So we have if we have C components and we have P phases, then we have so Cp plus 2 is the first one, and then we had P equations for C components, and basically was and this gives rise to total number of total number of equations. So if you know P minus 1 equations, you would obviously know Pth equation for C component. So this will make it C into P minus 1 from this. Then we looked at chemical equilibrium. So this is the number of variables Cp plus 2, total number of equations, which is nothing but, you can say, number of constraints, C into P minus 1 from the mass conservation. So this is the first condition. The second condition is chemical equilibrium, which we started to do. So basically what we were considering is we have two phases, phase I and phase K. The jth component, a small amount of jth component is transferred from ith phase to jth phase. So what we did was, we have, for the ith phase we wrote delta of Gi is equal to del Gi divided by del Nji into delta of Nji. This is equal to delta of Gi into mu Ji into del Nji. Similarly, for kth phase, so if this component J goes from I to K, the incremental free energy change for kth phase is del G K is equal to mu J k into del nj k. So this is, but we also know from mass conservation that del nji is equal to del nj k minus of, because the amount of solute which leaves jth phase, ith phase is same as the amount of solute which enters the kth phase. So if that is true, we can write del gk to be equal to mu jk minus of mu jk into del of nji. Okay. So if the total, now for system to be in equilibrium, the total change in free energy, which means dg, must be equal to 0. So that means del gi plus del gk must be equal to 0. So this is dg is equal to 0. So what it means is that substitute the, so this is mu j in I multiplied by del of nj I minus of mu j k into del of nj I, this is equal to 0. Basically what it means is that mu j I is equal to mu j k, and that is what we said earlier. So this is basically the proof of what we said earlier when we drew the common tangent, that in the first instance we saw it graphically, now we see it mathematically, that for a two-phase equilibrium or for a multi-phase equilibrium, the chemical potential of jth element in ith phase must be equal to that in the kth phase. So that is chemical potential of a component in various phases in equilibrium must be the same. Okay. So if you generalize, so for now for C number of components in P number of phases. So how do you write this? So let's say this is mu 1 phase 1, let's say 1 plus mu 1 2 plus mu 1 3 plus mu 1 p is equal, sorry, not, what am I doing, this is not plus, this is equal to, my apologies, so this is equal to. So chemical potential of a component in first phase, second phase or third phase is equal, and they are all equal from first to pth phase in all the phases. So if you now extend it for cth component, so mu c1 is equal to mu c2 and this is equal to mu c p. So basically what we are saying is that this is the transfer of C components in P phases. For all those transfers in multi-phase equilibrium, all these equations are there. So we saw that number of equations that you have here is, so total number of equations in the first case we saw total number of equations is C into P minus 1, and then we have total of P number of phases. Okay. So if you, from this condition, if you know, so you see that if mu 1 is same across all the phases, then it has to be true for all the P phases. If you know that this condition is true for, so we have total number of equations as P equations. So here I wrote here P minus C into P minus 1 equations. I should say P equations. Okay. And from this, since we are writing for C components in P phases, there are the conditions are mu1 is equal to mu1 p, and this is for all the C components. The total number of equations are is equal to number of components. So, you have number of components C multiplied by p minus 1, because by equality, if you know up to mu1 p minus 1, obviously pth is known. Okay. So this is C into p minus 1. So, total number of equations that you have is p number of equations from mass conservation and C into p minus 1 number of equations from chemical equilibrium, chemical potential, let us say equality. So, what is the total number of variables? So, total number of independent variables. So, this is nothing but n, okay, and the Cp plus 2 will be equal to m. So, we are saying this is basically m minus n. So, m is Cp plus 2 and n is C into p minus 1 minus p. So, if you now just do the math, this is basically C minus p plus 2, okay, C minus p plus 2, and this total number of independent variables is called as f. For a given system, it is called as degree of freedom. So, Gibbs phase rule is given as f is equal to C minus p plus 2. This is degree of freedom, which means number of independent variables, number of components, this is number of phases, and this is temperature and pressure, 2 extra variables. So, this equation is called as Gibbs phase rule. Gibbs phase rule, which correlates the number of components, number of phases with the degree of freedom under given set of plus temperature or pressure being 2 other variables. So, generally for metallurgical systems, or even materials systems, pressure is constant, and hence F is equal to C minus P plus . You can write this equation in another form. You can write this as F plus P is equal to C plus 1. So, F plus P, you can say, family planning, and C plus 1 is like one child. So, it is easy to remember. So, F plus P is equal to C plus 1 is the Gibbs phase rule. Now, let us see how this Gibbs phase rule applies to different phase systems in materials. So, now let us see how we apply this. So, let us say application of Unary single component system. For the single component system, we will begin with the iron system to begin with. So here we draw the phase diagram as a function of temperature and pressure. So this is temperature, this is pressure. So the phase diagram is something like this. Right, so this is Fe in liquid state, this is delta Fe, this is gamma Fe, this is alpha Fe, and this is epsilon Fe. So this is pure Fe. Okay. So now let's see what happens at different places. So when you choose a particular point in this region, let's say this region, this point A. Okay. So you can see that at this point A, so the phase equation was F plus P was equal to C plus 2. In this case, pressure is not constant, so it's F plus P is equal to C plus 2. So F is equal to C minus P plus 2. Number of components in this system is equal to, so let's apply for point A. So number of components is equal to 1, that's pure iron. How many are the number of phases? At point A we have only one phase, so P is also equal to 1. So F turns out to be 2. So we have two independent variables. So what it means is that whether you change temperature, whether you change pressure, you can change both of them independently, and still you can retain single phase equilibrium. So both temperature and pressure can be varied independently while maintaining a single phase equilibrium. Okay. Now if you go to this line, for instance, this line is the region on which you have, this is point B. On point B, what we have is, we have two phase coexistence. So gamma Fe liquid and gamma, for example, both of them coexist. At point B, it's again a single component system, C is equal to 1, P is equal to 2. So F turns out to be equal to 1, which means you have only 1 degree of freedom. So what it means is that, so if you look at B, for example, the moment you go, if you vary both pressure and temperature, let's say in this direction, you immediately jump into single phase equilibrium. In order to be on this line, the moment you change the temperature, pressure is automatically fixed. So when you want to be on this line, the change in one variable leads to fixing of another variable. So if you change temperature, the pressure is fixed to maintain that two phase equilibrium, or if you change the pressure, the temperature is automatically adjusted to maintain the two phase equilibrium. So you can say that only one independent variable. You vary temperature, pressure is adjusted automatically to maintain two phase equilibrium because you have to be on this line. Similarly, if you vary pressure, the temperature is adjusted accordingly to maintain the two phase equilibrium. So in a single component system, these are the two scenarios you have. At some point you can have triple phase, three phase equilibrium. So for example, pressure point like C, this is C point. At the point number C, at the point C, number of phases is equal to 3 and C is equal to 1. So F is equal to 0, which means there is no degree of freedom, and you can see that. If you move away from this point anywhere, whether you go here, whether you go here, whether you go here, whether you go here or along this line, you lose 3-phase equilibrium. So from 3-phase equilibrium you move into 2-phase equilibrium or single phase equilibrium if you vary either temperature or pressure, which means, what it means is that no independent variable. So this is like a point. So this is called as invariant point. Invariant means nothing can be varied, there is no change in any thermodynamic parameter that can be maintained to have a 3-phase equilibrium. So 3-phase equilibrium is possible in a unary component system only at a point, at a given point where 3 phases exist with each other and there is no change in parameter that can be made. So you can see that for a unary system, so invariant point means f is equal to 0. It is basically a point. When f is equal to 1, it is basically, you can say, a line. You move along a line, okay. So you adjust one parameter, second is adjusted automatically, and f is equal to 2 means it's a 2D or area based variation. So you can both vary temperature and pressure independently to get phase equilibrium single. So basically in a unary system it will mean a single phase equilibrium. You can apply the same logic to binary systems. So we can see in case of binary systems, so you have a phase diagram like this: temperature, composition, so you have liquid plus solid. If you look at point A here, so we look at point A, point B and point C. So we only look at point A and B because C is same as A, so which is same as A in terms of applying the phase rule. So at point A, so in this case C is equal to 2, you have two components A and B. Number of phases at point A is equal to 1. In this case pressure is constant. So F is equal to C minus P plus 1. So 2 minus 1 plus 1, that is equal to 2. So you have 2 degrees of freedom. So for point A, for single phase equilibrium, the pressure and so in this case it means temperature and composition, both temperature and composition can be varied independently for point A, that is when the degree of freedom is equal to 2, and this basically in a binary system implies a single phase equilibrium. For point B, or let us not say B because B is the composition. So anyway, that is okay, I think it does not matter. So let us say it is point B. So at point B, what we have is 2 phases. So P is equal to 2, C is anyway equal to 2. So in this case F is equal to 1. So which means only one parameter can be varied independently. So you can vary either temperature or pressure independently. So what it means is that if you are at point B, okay, the composition of 2 phases is given by these 2 points. So this is the liquid composition Cl, this is a solid composition C beta. If you vary temperature, for example to this point, if you vary the temperature, the composition is automatically fixed. If you are varying the composition, then temperature, now if you move along this line, if you move along that line, you vary the proportion, but your temperature, so composition remains fixed here, temperature is not. So, if you vary temperature, your composition is automatically fixed. So, the only variable is only one independent variable, because you move along a line. So, when you go to this point or the point below, the compositions are automatically fixed. So, the only parameter that you can, there is only one independent variable that can be changed in case of two phase equilibrium. You can apply the same logic to eutectic phase diagrams. In case of eutectic phase diagram, peritectic phase diagram, there is slight difference because you have invariant points, because you have three phase equilibrium, that we will see in the next lecture. So, basically to summarize, what we have done in this lecture is we have derived the phase rule, Gibbs phase rule, which correlates the number of phases, number of components with the number of independent variable to predict the phase equilibrium in a given system, or to maintain a phase equilibrium, what kind of variations can be done in the parameters and which parameters can be varied. And we have looked at the examples in the context of unary and binary system in case of isomorphous phase diagram. We will extend this to eutectic phase diagram in the next lecture. So, thank you very much.